afternoon session. So we just have one talk this afternoon session, and this poster upstairs on the second floor. And we're going to have Stella Biderman, who is the executive director of ElutherAI, a nonprofit AI research lab, talking to us today. ElutherAI has been a leader in releasing some of the biggest open source LLMs, including all the data and the training procedures. And more recently, Stella, in her work in ElutherAI, has focused on making interpretability research and learning dynamics of these large LLMs open to the wider research community. So in her talk today, she'll talk to us about what was revolutionized in the transformer revolution. Take it away.
Hello, is this on? Oh, okay, yes, good. Hello. So yeah, my talk is what was revolutionized in the transformer revolution. And I want to start by acknowledging it's a bit of a weird question to ask, because surely the answer is the model architecture. But that's actually, I think, arguably the least important thing that's kind of changed in the way people design large-scale AI systems in the past couple of years. So I want you to imagine an alternative world in which we have a very different understanding of chemistry. Now, in the real world, we understand when we have a chemical equation like this, CH4 plus 2O2 goes in, and we get this reaction that produces CO2 and two H2O molecules. This is not like a specific instruction on how to create exactly two molecules of water. This is a pattern, and you can put in as much of the inputs as you wish and get as much of the outputs as you wish in return. But suppose we don't know that. Suppose we view chemistry equations a bit like instructions that make like a fixed amount of products. A bit like recipes, actually. You can't take a recipe for a cake and just obtain a cake that is 10 times more cake because it won't bake right. And just kind of imagine that we live in a world in which that's how people view kind of all of these kinds of reactions. And then some research starts coming out. And the previous state of the art converts 5 units of A into 3 units of B. And this new research comes with two main discoveries. The first one that gets all the attention is the fact that they have a new recipe. It converts 3 units of A into 2 units of B. And this is substantially more efficient. It means that when you do your 100,000 individualized chemical reactions, you will eventually end up with more B than A. It will still take you forever, but you'll end up with more B than A. And they have a second observation as well. They realize that they don't actually need to run this one reaction 1,000 times or 100,000 times or whatever. They can just put all of the inputs together and get the corresponding amount of the output for any amount of input they want. And this kind of allows the process to be industrialized better. It allows you to save a lot of time because there's a lot of stuff that goes into setting up and running a reaction that isn't just the actual reaction itself, and that massively cuts down on the overhead. And suppose a couple of years later, we observe that production of B goes through the roof. Which is more responsible? Is it discovery 1 or discovery 2? I think the answer is definitively discovery 2. It's what enables labs to produce the resource at scale, even if it is slightly more efficient than it would have been had discovery 1 not happened. And in a world in which you can apply discovery 2 just to the original recipe, you still end up with roughly the same stuff. Maybe it's a little more expensive to get the amount of the resources you want, but it still works. I think this is pretty much a simplified version of what's happened in artificial intelligence. The transformer is a really interesting and powerful model architecture, but it's not the driving force behind all of the things that we are seeing today. And in fact, I think that in a world in which we don't have transformers, but do have all of the other discoveries that came alongside with them, we would still be having these conversations. We'd just be having them about different models and slightly differently. So what are these discoveries? Well, some of them we actually talked about yesterday on the panel. Converting unlabeled data into self-supervised data via next token prediction, originally masked language modeling, then next token prediction took over. In computer vision, they use a couple of different objectives. But the ability to take large amounts of unstructured, previously not valuable data and turn it into something that can be used has been massively impactful. The entire ability to train on the entire sequence simultaneously, I don't think this has ever been explicitly mentioned, but it's come up a couple of times. One of the big limitations with RNNs is that you only get update signal from a single token, and then you have to go get it from the next token. When we train transformers, we train on all of the input at the same time. And this has very big efficiency improvements. The ability to distribute model training effectively across hundreds of GPUs. There have been very serious HPC innovations and discoveries, some of it building on previous work, some of it pretty novel in terms of how to actually orchestrate a large-scale training run over thousands of GPUs. And finally, like the willingness to actually go do it has, I think, been a really big thing. The idea that this is something that you want to do and that you could just go pump all of your data into a very large HPC system and get out a very large model is a mindset shift from what people were doing substantially 10 years ago and even to some extent 5 years ago. But don't transformers outperform RNNs? Like we've seen this plot multiple times already. This is from the foundational scaling laws for neural language models from OpenAI. And yeah, it argues that LSTMs do not scale, their performance improvements do not increase with scale the way transformers do. And that's true for these models. But it's not true for other models. People have taken the advantages and the innovations that they've learned from building transformers and backported them to other things. So here is a model architecture called RWKV. I put a little box on the two plots around the RWKV models, and they match performance of transformers quite well across a variety of scales. And Mamba does as well. So this is from their paper. One thing I find perpetually amusing is that the Mamba paper says that Mamba is better than RWKV, and the RWKV paper, of course, says that RWKV is better than Mamba. But they both agree that like both methodologies are in the same ballpark as transformers. We see the same thing in image generation, also image classification, and a bunch of other areas. So here's a here's a table from a paper called Party, which was a text-to-image modeling paper by Google about a year and a half ago. That shows GANs, autoregressive, which is what they're using to describe transformers. These are like autoregressive transformer-based architectures versus diffusion models. Glide, Megascene, and DALL-E 2 are three very different architectures. Two of them are diffusion-based. One of them is transformer-based. What they have in common is that they all use roughly the same amount of input resources, data and compute, and they all get roughly the same score. Imagen and Party were built by two different teams at Google at roughly the same time. One of them is diffusion-based, one of them is transformer-based. And again, they use roughly the same amount of resources and get roughly the same performance. So the bottom line here, are transformers the best architecture to use in a wide variety of domains, applications, and modalities? I think the answer is yes. I think that there is compelling reason to believe that that transformers are a little bit better than RNNs or diffusion models, or I guess I should be saying like units, because diffusion is a training process, and CNNs in a wide variety of tasks. And that if you kind of have to pick one architecture to go with on all of the things that you want to do, I would definitely recommend using a transformer. But comparable advances to what we're seeing today can be made with previous architectures. And the marginal improvement that the models we have today have over the models that we had 5 years ago, 10 years ago, is not explained by, oh, now we're using transformers. It's explained by, oh, now we're using other things, in part because, as we just saw, other things that had previously existed are also seeing the same kinds of performance boosts. So people often ask, what makes transformers so magic that they've changed the way the world works? I think the most magic thing about a transformer is it's an absurdly efficient way to convert compute into useful work. The best one that we know of, I think, by a meaningful margin. And assume the word efficient here is going to raise some flags because we've spent a lot of time talking about how transformers are not efficient, especially with the sequence length. Here I have something very specific in mind. When I say it's an efficient way to do it, I mean that I have a ton of GPUs, a ton of data, and a stopwatch. And I want to get a very good model in the least amount of time on my stopwatch. I don't really care what the runtime complexity is. Maybe I don't even care what the flops are, except insofar as it impacts this. I have many, many hundreds or even thousands of GPUs. I have a very large pile of data, and I have a time limit, and I want to get the best model I can out of it. And that's something that transformers can do like nothing else. The fact that we can backport, so a kind of side effect, and something that's come out of a lot of the research on architecture in the past couple of years, is that architectural designs designed to improve performance are not actually very important. And the main reason for this is that they wash out with scale. it's really easy to take a transformer at the 350 million parameter scale and improve its performance, even significantly. It's very, very hard for that performance improvement to still exist at all, let alone to the same extent at the 10 billion parameter scale. Because the improvements we see as we build our models bigger and as we pump more data and more resources into them actually swamp the improved performance that we can get by being clever. There's a really funny corollary of this. The other side of this is that the architectural innovations designed to improve throughput are very impactful because those are what are driving us and giving us the ability to build a bigger model or train on more data in the fixed amount of resources that we have access to, which is mostly measured in time. There's a really funny corollary of this, which is that worse methods can make models better. So there's this alternative architecture for a transformer where instead of putting your attention and feed forward layers in sequentially, you put them in parallel. And so this was originally done by some of my colleagues, mostly Ben Wing, and they found that it had a small performance hit. Their model was 6 billion parameters, but it really sped up how fast they could train. And so we ended up going with it because it kind of gave us the most efficient use of our compute. And then evaluation of the trained model on various tasks of interest goes down when going up is good. So higher loss, lower accuracy. Not by a lot, but by a little bit, enough that you normally wouldn't want to use this. And then, so this text here is actually from Palm, Pathway Language Models. It's a 540 billion parameter model that Google trained. And they used it too. And what they reported was that although there was a small degradation in performance at the 8 billion parameter scale, which is the scale that we had trained at, it went away. And the speed performance stayed. Yeah? It can be. I don't live in a world in which data efficiency really matters. Which is a bit of a bold thing to say, but at least if you're talking about like large scale pre-training, like I can go get 12 trillion tokens off the internet very easily of very high quality data. And I mean, like Hugging Face a month ago put out a data set of 12 trillion really high quality tokens. I'm going to run out of money to buy computing resources before I get through 12 trillion tokens at the 10 billion parameter scale. And there's lots more data out there where that came from. If you are in a very data constrained use case, and there are cases where, especially like when it comes to fine tuning models, that is the case, that can matter a lot. But mostly I'm thinking here in kind of the limit of like, as you have more computing resources, as you have more access to data, that concern doesn't really come up very much. Yeah, and so they end up using it because they kind of extrapolated and figured that there'd be basically no performance hit, but they kept the 15% speed improvement. And 15% speed improvement is a lot when you're paying per dollar for every hour you're using your compute. And there are a lot of fiddly details here I'm glossing over. One really interesting thing is that like which architecture is better and by how much can depend a lot on the setting. So on the left, you have some experiments that I ran in 2021. On the right, you have a table from a 2022 paper. This is about comparing different positional embeddings. But I want to draw your attention to is the red line, which is no positional embedding. And I was really, really surprised when I ran this to find that it outperformed the sinusoidal, the original transformer positional embeddings, and was on par with learned and with T5 style relative positional embeddings. And that's that's roughly speaking what Haviv et al. Found as well. And in their paper, they showed that kind of the performance gap decreases substantially as you scale. So my model was only at the 530 million parameter scale and was with a very small data set. They scaled both up substantially, and they found that as they scaled, like again, like the performance improvement kind of really starts to go away as you scale things up. But at the smaller scales, especially, kind of the details can matter. And if you do have a reason to care about a model trained on a relatively small data set or with a relatively small amount of parameters, then these things can start to be very impactful, even if, in some kind of long run vision of scaling models and scaling data, they're less impactful. I mean, these ideas go back, like the inspiration for my experiments was work from Erie and Schmidhuber's lab, for example. Linear transformers are secretly fast weight programmers basically tells you that this will happen, that that no positional embedding will work just fine, but they didn't actually run the experiment. Yeah.
This is a bit of a pick, but like, this is perplexity, presumably.
These both show validation. Well, one shows validation perplexity, one shows validation loss.
I see. I was going to say like smaller differences in those metrics kind of become more meaningful the smaller the numbers get, right? Like reducing your loss by 1, if you have like a loss of 2 is like really good. Whereas if you reduce your loss by 1 and your loss of 8 is like, I don't know, it's a minor point.
Yeah, that's a fair point. If you go regraph their data and like put like a logarithm on the perplexity axis, the marginal impact is still going down. But all this is, so basically what I've said is that a lot of the architecture details don't matter. And kind of the main thing you want to do is pile compute into a model and make it really big. And this has kind of really changed, I think, the way that people should, let's say, ask research questions. Model design has become a lot less interesting. I've spoken with a lot of professors who used to be really interested in AI because they wanted to design novel architectures for specific tasks, and they're kind of like, I don't know why I should do this anymore. And I'm like, that's kind of fair. It's kind of become a HPC plus having a lot, like high performance computing research plus having a lot of money. But there's other kinds of questions that have become more interesting. So one kind of question that I'm very interested in is, for any particular analysis, like how do the results we find vary across scales? And in particular, I'm very interested in predicting the behavior of big models from the behavior of small models, and how you can predict the behavior of a fully trained model based on a partially trained model. So in 2023, my team built a model suite called Pythia to kind of study these questions because the existing public model suites were not really sufficient. And we were very interested in encouraging people to study how properties change over training. In particular, we released 154 checkpoints for every model in our model suite. At that point in time, we released the largest model in the suite is 12 billion parameters. We released more checkpoints for that one 12 billion parameter model than the rest of the world had released for all models of that size or larger combined up until that point. We really wanted people to look at learning dynamics style stuff. And so here's an example of an open question that kind of is shaped like this. So we know that models have a tendency to reproduce biases found in their training data. And it's very well documented. We also know that, like, abstractly, if you want to take a gender bias example for concreteness, there's some function that takes as input the percentage of doctors in the data set that are male, and will return as its output the frequency with which the model will assume that a doctor of unspecified gender is a man. And we know that this is a non-constant function. It's not f of x equals x. And that as soon as you get a little bit of 50%, the model starts actually exaggerating the biases and over-assuming based on kind of the raw frequency rate. But that's basically all we know. And I think the shape of this function is very interesting in this problem, but kind of as a more general principle as well, especially because there's an interventionalist variant. How do I modify a data set to deliberately end up with the property I want? So you give me a data set and I look at it and I say, oh, I think if I train a model on this, it's going to have, oops. Apologies. It's gonna assume that 90% of doctors are men. I want that number to be like 65%. What do I actually do to the data to make that be the case? And I think this is especially interesting if you start off with a partially trained model. So you have a model that's training and you observe that its behavior, whether it's in bias or some other context, is outside the range of values that you find appropriate. So you pause it. And then you have to ask yourself, what do I actually change to change the behavior? So I've run some very inconclusive experiments on this in the past. This plot's from the Pythia paper. We rewound the models for the last 1/7 of training and replaced every masculine pronoun with a feminine pronoun. And then we finished training out the models again. So the original models are the solid lines. The intervened models are the dashed lines. This is the y-axis here is a measure of binary gender bias. And for smaller models, we found there was basically no impact at all. But for the larger model we looked at, the 6.9 billion parameter model, there was one. So I have this like vague intuition that we know that small models converge in loss space much faster than larger models. Maybe there's a sense in which it's converging in bias space as well, that there's a certain amount you have to go back, or that after a certain amount of training, it's very, very hard and requires massive amounts of resources to do it. Maybe with a small amount of rewarming, you can get out of the particular loss space. And there's a lot of, I think, very interesting questions here, both from an applied point of view and from a theoretical point of view. Like this is at the end of the day, like a learning dynamics question of a shape that's been studied by ML theorists for quite a long time. Another kind of example of the kinds of research that's become things that people have studied is from a paper from last year, where I'm interested in understanding what models are going to memorize. Now, up until this point, basically the entire literature on memorization said, okay, memorization is a corpus level statistical property. You know, we train a model on data and 3% of the data is memorized. And if you make that number go down, it's good. That doesn't really respect what people care about, though, in part because some memorization is actively good. If you put into a model 2 + 2 equals, or George Washington was the first president of you really want the next couple of tokens to come identically from the training data. And if that doesn't happen, something's wrong. Memorization is bad for certain types of data. And kind of more specifically, it's bad for, in the context of language models, it's mostly bad for spreading people's PII and for kind of telling on yourself when you trained on copyrighted data that you weren't supposed to train on. But if we can predict which specific data will be memorized before we train the model, we can use that to inform decisions about model training. We can use that to inform decisions about data set design. You know, if you have some kind of way to perturb the model training process so that maybe even just randomly different things get memorized, and you can check cheaply what is going to get memorized before you train, you can end up with a model that you find more desirable. So we've run some experiments about this using a very simple predictor. It works like okay. It doesn't work in the way that you need it to work in practice because people care a lot more about recall than precision. But this is, I think, a very promising open avenue, and there's been some follow-up work in this direction as well. Yeah. Oh, so yes. So this is like the stupidest thing possible. We take a cheap model and we measure what it memorizes, and we assume the big model memorizes the exact same stuff. And so that gives us a classifier over the data set that tells us, that classifies it as memorized versus non-memorized. And then this is the precision and recall of that classifier. So in both, on the right-hand side, left-hand side, we're predicting the behavior of a fully trained 12 billion parameter model. On the right-hand side, we are looking at, over the course of training at the 2 larger models in the suite. And so like the precision numbers are very high, but that's kind of because all the models memorize mostly the same stuff. It's more problematic that the recall numbers are very low. And roughly the thing to know about training costs is that the cost of training a model grows linearly in the number of parameters, and it grows linearly in the number of tokens. So if we have a budget for training a 12 billion parameter language model, we'd like to be able to look at something that costs like 1/10 that and get a reasonable predictive accuracy. But here the recall is 50%. So there's tons of stuff that we are incorrectly classifying as not memorized. And that can pose a problem because of the kinds of specific cares that memorization brings, where you really do want to have a high recall because you get in more trouble for having false negatives than false positives. And again, like over the course of training, we see that you need to do quite a lot of training to get a pretty high reasonable score. Even like this is the first entry in the table. This is already 1/7 the way through training. So this is, not quite. This is about the same relative cost as this model. And the numbers are in the same neighborhood. We were basically pitching this and putting this as a baseline and saying, this is a cool thing that people should start looking at. There's been other stuff where you're looking at the actual contents of the data. Naomi's worked on that. There's been stuff about looking at data order and other kinds of questions to kind of improve the scores. And like it's improving. And I do think that this is a thing that is tractable. Like you are going to be able to predict with reasonable confidence a lot of what gets memorized before you train the model. It's just a matter of figuring out like what the right way to do that is. One of the big open questions here is what does order matter when it comes to memorization? So I've claimed in two separate papers that the answer is doesn't. So specifically the question is like, does the position within the training data set influence whether or not a specific data point is going to be memorized? I've written two papers in which I've claimed it doesn't. There's a recent paper that won a best paper award at ACL like last month that claims it does. This is a really great place for theorists and more mathematically inclined people to get involved, because basically like we all have the same data. They're like this paper by Leshy et al. Literally analyzed data I released from my study. They just had a different analysis and found different results. And so this is an area where, like, again, like it's mostly just remembering about statistical models and getting a better understanding of what the right way to evaluate these things are is really helpful. Especially because as much as machine learning people, applied machine learning people like to say so, they're really not statistics experts. Yeah. Sorry?
For example, if you have continual training, then there's a problem.
So yes. So I mean, I don't have a short explanation. I like did some research as to what the right statistical tests to use were, and I ran them, and it said the answer was no. And these other people did other research as to what the right statistical approaches were, and found a different method, and found that the answer was yes. And when it comes to like continual learning, like forgetting is a problem, but it's a problem that's been substantially alleviated in like the past couple of years, both through like data replay, like reincorporating pre-training data into the continual learning process, as well as like more careful rewarming up of optimizer states. In the emergent and predictable memorization paper, we do actually look at the forgetting of memorized examples. We find a really interesting pattern, which I don't have on any slides, but we take like the earliest checkpoint we look at, and we say, only for these data, like what percentage of them are going to be memorized at future checkpoints. And then the next checkpoint we look at, it's gone down a whole bunch, but then it gradually climbs up again. And I think this is in part a side effect of the model getting better at language, because the way that we measure and conceptualize memorization in the literature is like kind of faulty. It basically boils down to like, can you reproduce data identically from the training data? But as model capability improves, there are some examples that you should be able to reproduce identically. So a really good example of this is software licenses. Basically, like if you've taken Apache 2.0 software license, they basically all look the same. They're kind of like a template, and you fill in a couple blanks. If I show you the first 50 tokens of an Apache 2.0 software license, and you've seen enough of them, you're able to reproduce the rest of the file exactly, because all of the information that you need to fill in the blanks is found in like the first 50 tokens. So yeah, so like the way people understand memorization in large language models is going to classify this as memorizing, once the model has this capability, every Apache 2.0 software license found in the data. The problem with this is that performance is also 100% for things it hasn't seen ever. So if you take a software license that was not found in the training data, and you show it the first 50 tokens and say like, produce the rest of the document, because that's the methodology people use to evaluate memorization. It's going to be able to do that with 100% accuracy, because all of the information is self-contained once you have like an understanding of what the template looks like. So I think at least to some extent, the like rebounding effect that we've observed is due to poor conceptions of what it means to be memorized. And this is like another place where I think there's a lot of room for like better clarity of thought. How much time do I have? The timer went away. Okay. Yeah. Look at this. Yeah. So the last paper I want to chat about was actually just this morning got into NeurIPS. I'm very excited. It's Kurt's first author paper ever. So there's a lot of like mechanistic interpretability research that builds these like computational circuits inside of neural networks and uses them to kind of reverse engineer the behavior of language models. And basically every paper that's ever done this like looks at like one or two models and looks at the fully trained model. But there's like some important questions here, like how stable is this across the course of training? If you do this on a small model, can you extrapolate the results to a big model? A lot of the motivation for this kind of work is that people want to build tools and techniques that's going to help them analyze the behavior of very large models where it's hard to do this manually. This is a very, very manual task, and the amount of work it takes goes up very quickly as the model gets bigger. So in an ideal world, you'd like to be able to figure out like what the computational circuit is on a small model, and then extrapolate that behavior to a larger model. And we found some really interesting results. So firstly, we found that you do have roughly the same circuit, and that across different scales of models, the circuit components emerge at like roughly the same place in training. This is similar to like the induction. This is in one case even a reproduction of the induction heads research at Anthropic, where they found that like induction heads emerge at the same kind of point in training, no matter how big the model is. And then we looked at which actual neurons were involved in the task at different points in time and found substantial fluctuations that at some point in time when the model had the capability, certain neurons were involved. And then over the course of training, the model preserves having that capability, but which neurons are actually doing the activities changes. And that despite the fact that these individual neurons are changing, the algorithm that the model learns is in fact stable. So I think this tells you something very important about like what you can and cannot extrapolate. So if you care about knowing the algorithm the model is going to be using, that's something you can have reasonable amount of confidence on. You can measure that early in training and be like, okay, and I know what algorithm the model is going to be using. But if you want to, for example, intervene on specific weights, change the model internally when it's fully trained, you're not necessarily going to know by the end of training like which specific neurons you should intervene on and which components are involved unless you go reanalyze it. Yeah.
Analysis independent, like for each checkpoint during training, it's like the which neurons you're tagging as meaningful for the task?
Yes.
Is it possible that there is redundancy throughout? And like, did you check whether like whether, okay, if I assume that this neuron is involved with the task as it is at that checkpoint, then is it still, like if I treat it as involved, is it still behaving similarly in terms of that task earlier? Are you exclusively looking at independent checkpoints? Because it could then just be an artifact of variation in like what, I don't know what model you're using, like an SAE or something.
So this is like on Pythia, we're taking a couple kind of standard examples and so we do both. So we're not using like SAEs or anything here. Actually, I have a rant about SAEs I'm happy to share with you later. So we do both. I don't have any plots from the paper in the slide deck.
Just based on gradients then? Or
so like
yeah.
Sorry?
Do you just decide what's involved in the task based on the gradient?
Via activation patching mostly. Like we're copying the techniques from existing papers, like we reproduced the IOA paper, for example.
So you can't transfer activation patching outcomes across different checkpoints.
Correct, but you can like tag those neurons and then say, okay, if I do activation patching later in training using the same specific neurons, am I going to see the same effect? And the answer is no.
Okay.
Yeah, and yeah, so we do take the things that do the circuit early in training and look at the extent to which they do the thing throughout the course of training, and then we take ones that do it at the end of training and look at how the extent to which they do it over the course of training. We have like a couple of plots about that in the paper. Those are, I think, specifically on IOI because that was a lot of work that we didn't get around to for all the things. Yeah, I have a bunch of backup slides, but this was kind of what I wanted to share and answer people's questions. Yeah, what's up?
I'm really interested in result number 2. Like, can you identify like the lazy neurons versus the active neurons beforehand, or is that a data thing? Like after the data is absorbed, then just the data is getting some.
So yeah, so this is only after you've trained or partially trained the model. At initialization, all neurons in a single layer are interchangeable, so they're identical. Yeah, so we take a partially trained model and we go identify which neurons are activating and are, we believe, causally responsible for the behavior that the model has. And then that set of neurons is like, you label all the neurons in the model and You go do that later in training with the same set of labels, and you find that the indices are different. Yeah. Any other questions? I have a couple more slides about similar-ish research, also a couple slides about parallelization, but I also wanted to give people a chance to answer questions. Yeah.
So this is a neuron level. What about at a, let's say, like a head level, or which MLP layer level is it changing? Just within neurons, the specific part of the network.
I don't remember off the top of my head. I can go look in the paper and let you know. We do actually report like the exactly where in the model it is. I just don't remember, and like I said, I don't have the specific plots here. Okay, yeah. Another kind of ongoing research project that I'm very interested in, I think kind of, like I said, is enabled by this different view of stuff is we've heard a lot, including earlier today, about emergence. There's this weird phenomenon where on the one hand, you can very, very easily predict test loss as a function of compute. This is from, again, Kaplan et al. And then when you look at these actual evaluation metrics that someone might care about, you get this hockey stick effect. So what's going on? So there's a paper by Riley and Schaefer and a couple other people that hypothesized that continuous metric, but discontinuities in the way we compute accuracy scores is kind of the culprit here, and that's inducing this behavior. And so my lab actually partnered with him, a follow-up to that, where we kind of investigate this. We found a kind of a slightly different story. So what you see here is the process that it takes to go from kind of the raw model outputs, or that's unfair. This is, so you start with loss being highly predictable, you end up with accuracy being very poorly predictable. So what are the kind of transformations of that evaluation metric that you have? Well, if you actually just start with loss on the benchmark sample, it's still highly predictable. And so the first thing you do is that you negate and exponentiate, you get a probability of the correct answer. Now, evaluating language models is really, really hard for a bunch of reasons. One of the biggest ones is that the best automated tools we have for telling if two sentences are semantically equivalent are the very models we're trying to evaluate. And different methodologies, different approaches to evaluation kind of have different ways of getting around this. One that's really common is to do multiple choice questions and to just throw out everything that's not one of those multiple choice questions. So you give the model, 4 answer choices, usually in context. We say, answer which of these is the answer to the question, and we only evaluate the probability mass assigned to each of those particular questions. So this is a vocabulary restriction in which we have probably being only renormalized and assigned only to specific questions. And then finally, we compute the argmax and get the accuracy. And what we find is that all of these degrade the correlation between compute and performance. These plots are a little bit complicated. Ooh, that is incredibly pixelated and illegible. Okay. So this is a, generally speaking, an area under the curve representation. The closer to a full box you have, the more predictable the behavior is at a large scale compared to the small scale. This is what you get for different model families, looking at both scaling over data for models with checkpoints, as well as scaling over model sizes. So this is the log probability of the vocabulary of the correct choice. So like unrestricted vocab. And outside of this one model trained, that's kind of weird. You have very good results. These are basically as good as you get for kind of regular loss prediction. And then when we restrict the vocabulary to looking only at the probability of the correct choice, it flattens out substantially. And this means that there's much, much less predictability of the behavior of the model over the course of scale. And then we go and we compute accuracy. So Breyer score is something that the original scaling laws or Mirage paper recommended as a potential alternative. We find both Breyer score and accuracy to further degrade the correlation, as well as discretize it. So I don't know if the pixelation makes this impossible to see, but they've become much more step functions. It's finite data points, so it's all step functions on a line plot. But the steps have become a lot more pronounced. And so kind of, in Schaefer et al. 2023, they find that there are contexts in which Breyer score is helpful. We find that there's a bunch of contexts in which it's not. We run this kind of analysis for a dozen standard widely used NLP benchmarks. This particularly is ARC Challenge, which is a popular one. And so like, I think this is very interesting, kind of mapping how the metrics change and how that change kind of causes the degradation of performance. And this also kind of pitches a couple different interesting potential follow-up research questions. So one of them is, can you design a metric where this doesn't happen? Can we understand why this correlation is getting degraded on a statistical level and design different ways of evaluating models that makes this not happen? And I think that's especially interesting if we're able to design. So nobody's like super attached to ARC Challenge. Nobody thinks that that's like the gold standard for performance evaluation, but they think it's like roughly correlated with the thing that they actually care about. And so if you can design something that's going to be more predictable, more consistently predictable over the course of scaling, and also like roughly as correlated with the thing in the world we actually care about as our challenges, you know, like a ARC Challenge variant that is specifically designed to be more predictable, there's a huge amount of value there. There's a huge amount of value there for people who train models, so they can be more confident in the fact that the model setup they're using is going to scale and give them, you know, high benchmark scores that they can brag about to their friends and co-authors and investors and whoever. It's really helpful for regulators. One conversation I have a lot with people in various governments from a regulatory point of view is like, how do we know what the performance of like, you know, GTP7 is going to be like? They're going to promise us the moon. Like, how do we know if they're actually going to deliver that? And I mean, the answer to that is in part, you can't, because the definition of like the next OpenAI GPT model partially depends on like how much performance improvement they want to see in the next version update. But even if you like were indexing this by like the amount of compute expended, the data set size, the parameter size, it's a very hard question because we're currently struggling to predict performance benchmarks for models as they scale. Yeah.
In this case, it looks like if you just take the probability of the correct choice, then this makes it very predictable.
Yes.
Are you saying there are other characteristics of evaluation that doesn't satisfy that we want, or that this doesn't always happen?
So I think that the situated studies on this are like kind of not great, and so like the evidence is more equivocal than other people might say. But there's several papers saying that loss on an evaluation benchmark is not adequately capturing the like knowledge-based thing that we want. So although this is predictable, we shouldn't actually care about the value nearly as much as we care about the value on the benchmark. And so ideally, we'd have both. We'd have something that is as correlated as loss on the evaluation set, but also has the kind of correlation with the thing in the world we care about. The reasoning capabilities in this particular case that the accuracy has. And like I said, all of the validation studies of LM eval benchmark, the validity studies of LM eval benchmarks is like kind of sus. This is kind of a general attitude that people have in the current literature consensus, at least. Yeah. Oh. Any other questions about these, about other things, about? Okay. Thank you very much.